that's a neat problem. Okay, problem 1913. Problem 1913 says, what temperature do you need in order for a cylindrical rod of tungsten with a given diameter of 15.025 for that rod to fit perfectly into a plate of steel that has a hole of 15.000 millimeter. So basically what we're trying to do is you got some plate and the plate has a hole in it. The hole has diameter 15.000 and we want to shove in that a rod which is just slightly oversized. Right, this is 15.025. So what we're going to do is we're going to change the temperature, and in the process of changing the temperature, the difference between the thermal coefficient of expansion for those two will allow us to fit them to the right size. We stick them together and then we can cool them or heat them back to their desired temperatures. Okay. This problem is relying on a linear change in the material size as a function of temperature. So we have this equation, alpha L T F minus T0. Okay, and I'm going to call this S, S, or W, W, depending on whether it's steel or tungsten. They have the same final temperature, they have a different thermal coefficient of expansion, and they have a different initial diameter, but the same final diameter. So we can get dF is equal to moving these initials over this side, we get D0 S 1 minus alpha L S TF minus T0. So the steel on one side, and on this other side we can say D0 W 1 minus alpha L W TF minus T0. So we have this equation equal to this equation, and that's basically the condition for the problem. This is known, that is known, that is known, 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 known. And you solve for the temperature. And you get TF is equal to 7.4. Here you see. I think this is a neat problem. I think I'm going to put this on the quiz on Monday. Okay. 19.4. This is a thermal coefficient, or sorry, thermal transport problem. This is a problem asking for what is the heat flux through brass that is 7.5 millimeter thick, given a temperature gradient that's defined. One side is 150 degrees C, the other side is 50 degrees C. And we're staying as a steady state, which basically means that we can use the thermal transport equation we had that looks very similar to Fick's first law, that Q is equal to minus K delta T over delta X. And this is our heat flux. And great. So, delta T, we have our two temperatures. Recognizing, of course, that K is 120 watt per meter K, because that's in Kelvin. These also have to be in Kelvin. Remember, units are everything. Well, they're not everything, but they certainly are helpful. And if you have the wrong units, everything's gonna go wrong for you. And same thing here. This X, that's in meters. So even though this is given in millimeters, put in your solution in meters. And doing that, you get Q is equal to 160 times 10 to the 6th watt per meter squared. Next question is, what is the heat loss per hour given an area? Well, this Q is watt per meter squared. Watt per meter squared, watts are joule per second. So we have, 1.6. We have 1.60 times 10 to the 6th watt per, joule per meter squared second. Well, if you multiply that by 0.5 meters squared, meter squared goes away, and that's going to give you a solution which is joule per second. And then you'll have to multiply by 60 times 60 second per hour to get it in joule per hour. And doing that, you wind up with 2.88 times 10 to the 9 joule per hour. Question now is, what if heat loss were stored to lime glass instead of brass? So basically we're saying, what happens if we change K? So let's go back here and say heat loss is equal to QA, that's heat loss per hour, QA times 60 times 60. Well, we can substitute in, this for Q and get loss per hour is equal to negative K delta T delta X A times 60 times 60. And doing that, change this to what is soda lime glass? Soda lime glass is 1.7 watt per meter K, and that gives you a solution of 4.08 times 10 to the 7 joule per hour. which it roughly doubles the heat loss, or doubles the loss per hour. Ah, no. Sorry. Ha! My mistake. 10 to the 9, 10 to the 7. So this is 2 orders of magnitude slower. Whew. Thank goodness the world obeys my intuition still. Yeah, 2 orders of magnitude slower. So soda lime glass is significantly more insulating. The next part of the problem says, what if the thickness is increased to 15? Well, we still have the same equation, so we can go, let's pick another color, let's pick pink here. We can say negative K delta T over delta X A 60, and now change T to 15 times 10 to the minus 3 meters, and doing that we get heat loss of 1.44 times 10 to the 9 joule per hour. So basically we're just taking the same equation here and working with it. Okay, problem 19.26. We say that we have a steel wire that is stretched until it has a stress of 70 megapascal. Whoa. And that's at 20 degrees C. If we hold that length constant, how do we have to change the temperature until the stress reduces to 17 megapascal? So this whole problem has to do with thermal stresses, and in this class we've been dealing with thermal stresses surely through this expression. So, is that right? No. So we want to know the change in the stress associated with changing the temperature, and this has to be equal to 70 minus 17 megapascal. Of course, this has to be compressive, so we actually need to minus 53 MPa. Young's modulus around 200 gigapascal for steel. Alpha L is equal to 12.0 times 10 to the minus 6 inverse degrees C. Our initial temperature was 20 degrees C. This we're solving for, and we get TF is equal to 41.3 degrees C. And finally, I'd like to look at problem 19.28. And this is a neat problem because it includes the mechanics in addition to thermal properties. So it says two ends of a cylindrical rod of nickel that is 120 millimeters long and 12 millimeters in diameter are held fixed. So we got this rod and we're fixing it, and then it's initially at 70 degrees C. If we want the rod to be cooled, and in the process of cooling have the diameter shrink by 0.023 millimeters, what temperature do we have to cool it to? So this is kind of neat because there's two parts to the shrinkage. The first part is a thermal contraction. Thermal, what do I call this? Thermal coefficient of expansion, or thermal expansion. And the second part has to do with the change in the cross-sectional area due to Poisson's ratio. Right, because we're holding this fixed, and when the rod wants to change length but can't, that's necessarily going to apply a longitudinal stress, which will then result in a lateral strain. So let's start with part 1. Delta D1. That delta D1 is just the thermal expansion / contraction, so that can be expressed LTF minus T0, right? So that's something we can find, and we know all of the, well, we don't know that, but we know this, and this. The next is this Poisson ratio effect, which the Poisson ratio effect is going to be d2 over d0 is equal to, this is going to be the transverse strain, but that transverse strain is equal to negative Poisson ratio z. That is the longitudinal strain, and you say, well, it's not being strained, it's not moving. Well, it's strained because there is a stress being induced due to the thermal expansion. So this longitudinal strain is associated with the thermal stress and the Young's modulus, which means that let's just write this as negative nu stress over E. Okay. And this thermal stress, that thermal stress is E alpha L T0 minus TF. So that means we can put this into there, which gives us delta D2 is equal to minus D0 nu alpha L T0 minus TF. So we now have an expression for the thermal expansion / contraction and the thermal, the change in the cross-sectional area due to thermal stresses in the longitudinal direction. Which means that delta D is equal to delta D1 plus delta D2 is equal to D0 alpha L Tf minus T0 plus negative D0 nu alpha L T0 minus Tf which we can now rearrange to D0 alpha sub L Tf minus T0 1 plus nu. So D0, we know that's like 12 millimeter, right? Alpha L is 13.3 times 10 to the minus 6 inverse degree C. Tf we're solving for. T0 is 70 degrees C, and Poisson ratio for nickel is 0.31. And this is 0.023 millimeter. Which means that we can find Tf is equal to minus 40 degrees C.